Welcome back to the channel. My name is Jonathan Riddell, and today what we're going to do is we're going to talk about how to write code in parallel in C++. So this is something that might seem a little bit intimidating, but as it turns out, getting certain programs about 90 to even 100% of the way to fully utilizing your CPU, it's actually quite easy. In this video, I'm going to show you a quick crash course on how to write parallel programs in C++. Specifically, I'm going to show you how to use the other cores on your CPU. This is actually surprisingly easy to get started, so it's definitely something you shouldn't be intimidated by. But before we jump into this, I recommend everyone to go check out my Discord channel. It's a growing community of researchers and students. The community is focused on scientific computing and condensed matter physics or statistical mechanics. And it's turning into, sort of quite a good resource to have discussions on things that are important to people in these spaces. With that in mind, let's actually jump into the code and show you how easy this is. All right, so I have my multi-processing folder set up, and inside of it, I have my makefile and demo.cpp. And let's quickly look at the makefile. It's going to be slightly different than the last makefile. I'm still including eigen if you watch that video. This part isn't important for this demonstration, but it's just sort of something I always copy and paste. The thing that's important, though, that's different is I'm going to also pass the flag -f OpenMP. Okay, the library that we're using is called Open Multiprocessing. It should come out of the box with whatever compiler you have, so it should be easy to follow this demonstration. So if you go into a standard .cpp file, I have my main. I'm allowing myself to pass numbers. We'll comment this out, but eventually we'll use it for the demonstration in the future. Let me delete this using namespace eigen. And for the demonstration, we're going to need IOStream so we can print things to console. And then for OpenMP, we include omp.h, and I'm going to be using some of the math functions, so I'm going to include math.h. Now here I am basically just I'm defining pi as the arc cos of -1. This is just so that we have it. You can also from math you can use m_pi, but old habits. So it's not important which one you use. So to initiate a parallel region, what you do is you will do #pragma. These are pragma directives, OMP parallel. And now what happens is, with the current way that we're writing this, OpenMP will spawn basically the maximal number of threads by default to run inside this scope. So inside these curly braces, you now have a parallel region where a bunch of different threads are running. So a quick way to see that we have a parallel region with a number of different threads running is to actually just print out their thread ID. And this is how you do that. If you want to know which thread you're sort of talking to in the program, you say omp get _thread _num. And here I'm going to create a end line like this. So doing that, if I make demo now, let me increase this so you can see. You can see that all of my threads are printing out their thread ID number. So I want you to take a few things away from this. First, which thread gets to the print statement first is not deterministic, right? It's sort of, threads are doing different things, and so this is not something you can actually predict, right? So this is the sort of master thread or the main thread, but you can see, 9 gets there first, and then 10, and then 6. Now, another thing interesting happened here for this last run, and this is what's called a race condition. And basically what happened is when thread 5 got to the print its thread number, that was around the same time that the instruction for print 7 got there. And this was done so fast and so like in line with each other that actually this was executed by 5 and 7 before the end line was able to be executed. And this is what's called a race condition. This is behavior that we probably don't want. We want this whole line to be executed, or at least I do, just so that the printout is sort of, so that the printout looks nice. We want this to be executed in a way that we expect. And so we expect that this whole line is executed all at once, and by default, we don't get that behavior. So to fix that, what we can do is we can introduce a region that we call a OMP critical region, like this. So let's cut this, put it in there, and when I make demo, output demo, now you can see that it will always come out nicely. And what critical is basically doing is it's basically saying only one thread can enter this region at a time. So it'll start a queue, and it'll say once thread 1 is finished with this command and it exits this scope, okay, now the next thread can come in, basically. There are other control structures like this. So for example, you can do single, which is basically telling the code that you only need a single printout, basically. So it'll basically pick the first thread to get to this line, and that will print out its thread ID. Right, so that's 3, that's 4, that's 8, that's 0, right? Now, by the way that you can control how many threads, because you might not want all of your threads dedicated to your program, is to do this. So for example, if I set it to 1, it'll always be 0. If I set it to 2, maybe this is a bad example because I have the single on, we might still get 0. But you can see that let's quickly change this back to critical. So all of the threads get printed out. Right. So if you see 2, you get 0, 1, 0, 1. And then of course I can go higher. So let's get 6, and we get 0 through 5 printed out. So that's pretty great, right? Now something that you need to know is that this OpenMP has a framework that basically has shared and private memory between threads. Now, sort of a way to think about this implicitly is that if I declare a variable out here, this variable is shared in the way this current program is set up. And what I mean by shared is that all of the threads can see this memory address. So they can all modify X. They don't have a private copy of X. They can all see and update X. Now, if I was to write int Y in here, this is private. Okay, and basically what that means is that if I have thread 0 and thread 1, each of them has their own unique copy of int Y, and they can't see each other's Y. So, for example, we could say int X is equal to OMP get num thread, right? So now it stores the thread ID. Let's get rid of this for a while. And instead of that, we can do X here. Now this doesn't actually make sense. What we actually want to do is something that looks like this. And now X is private and it has the thread count, and it has the thread ID that you want to be printed out. And of course it works just like before. Now, what if though I wanted, for example, for bookkeeping reasons, to do something like this? Now, this by default is shared, and we don't want that because basically what that will do. Actually, let's just do this just to see what it does. Right. So basically, what happened is that 10 was the last thread to be called to assign to X. Or not the last one, I guess. I guess 3 was perhaps the last one, or who knows how this was actually executed. But basically, a bunch of these print commands happened when X was assigned to 10, right? But if I do, in fact, if I'm insistent that X is declared out here, I can actually just tell the code that it's private, right? And then now X will be private to all of the threads. Does that make sense? Hopefully that makes sense. But basically, with OpenMP, you always have to be aware of whether or not a variable is shared or private. And by the way, you can do as many as you want here. So I could do XY. There are more declarations here. I'm not going to have an exhaustive crash course of OpenMP. There's more advanced things that you can do, but this is basically the gist of it. And if you want to explicitly tell me or tell the program what's shared, you can also do that. So let's actually do this. Do this and do this. One other directive that is sometimes useful, the pragma OMP master directive, and what this will do is it always picks out the 0 thread. So if you always want a specific thread to execute certain commands, this is the way to do it. And so this is in contrast, just to summarize, right? So we have the OMP parallel. This starts our parallel region. And then we have critical. So that's one thread at a time. Then you have single, sort of first thread to arrive, does task. And then you have master, which basically takes 0 thread and does whatever task you want to actually do. All right, so this isn't really the power of threading, though. The power of threading is basically doing for loops very fast, or it's doing independent tasks very, very fast. But before we get to for loops, I just want to say, one thing to note is that these pragmas are basically ignored if you're only running with one thread, or if you're not compiling with OpenMP. So it's sort of harmless to extend your code with OpenMP. It's not bad practice, even if you sometimes only want to run in serial for some reason. Okay, so now that we have sort of the gist of, these are the threads, this is the memory layout, which is very crash coursey. I did not go into as much detail. You should definitely look up documentation if you have questions, or of course, come to the Discord and chat. Let's actually solve a problem where we need a for loop. Now, the problem that I'm going to solve is a quick integration problem. We are going to basically solve the problem of integrating from 0 to 1 sine of pi x, and we'll do it naively with, and we know the answer to this, by the way, so that's 2 over pi. And I'll bring the pi over here, right? So that our answer should be 2 at the end. That's why I have the pi prepared in the program. Okay, so what we're going to do is we're going to do a Riemann sum, and we'll do n total points, right? So we're going to do a sum. So let's call this number s, and so the s will be 1 over n points times the sum of sine pi over n, basically times an index. So let's call it m to n minus 1 m, right? And so when we compute this, we'll get out the number 2 over pi, and then we'll multiply it by pi. So let me just put a pi here, and we'll get the number 2. So this is the math problem that we'll quickly solve. It's very naive, but at least we can scale it quite easily to show the power of multi-threading. And we'll also show, some of the drawbacks, some of the things that you need to be aware of, because throwing more threads at a problem doesn't always make the problem faster. There is overhead to spawning threads and to using threads. Okay, so let's allow us to input the integer n, which will tell us how fine-grained our Riemann sum actually is going to be. And let's call double sum is equal to 0, and let's start our parallel region. To do a for loop, it's very simple. You do #pragma OMP4, And whoops, so then you do 4, just like you would do a normal one. 4 int m is equal to 0, and we're going to go up to n as our formula demands, or n minus 1, as this does, and m plus plus. And basically, it's quite simple. We'll just do it in a way right now where we'll just do the sign terms, right? So we have m times pi, or let's do it in a nicer way, pi times. I'm going to cast m to a double just so it doesn't get confused and do integer division here. And basically, what we'll do just to start us out is we'll do the answer. We'll print out sum. We'll multiply pi times sum divided by n, right? And so that should give us 2 if n is sufficiently large. And let's end line here. So the first thing that I want to do is I want to run, and let's do it for 100. Okay, so we can see, actually, I don't like how much precision there is. Let's quickly change the precision. Let's do 15 of the printout. Make demo, and we'll run it in serial again. Okay, so that's our accuracy, and also the code is very quick, but we can go to 1000. Okay, we're still not perfectly accurate, and we'll go to 10,000. Okay, we're getting more and more accurate, so maybe this isn't, in terms of a research project, this probably isn't the best use of resources. But okay, so now the program's actually taking a little while to compute, and we're basically there, right? Like, I mean, like, this is basically numerical precision. But let's do just a little bit more, so the program actually takes time. Okay. We didn't get any more accurate. In fact, this is probably numerical error, sort of rounding up, but at least we're doing a task that takes time now. Now, if you're watching this and you've been sort of grasping what I'm saying, what do you think is going to happen now when I actually turn on multiple threads? Quickly thinking about what's going to be happening to the term sum here. So let's make this smaller. And let's turn on 2. And you see right away that now the answer is wrong. And what's happening is that multiple threads are trying to perform this operation at the same time. Now, one way to fix this would be to, let's call them 3 different ways that you could fix this. The first way that you could do, for example, would be to have a global sum that's shared, and then introduce a local one, and actually only sum up the local ones so that they're local to the thread, and then later, once the problem is done, you could add them all up to the global shared one, right? Okay, we're not going to do that. Because there's basically there's a fancier or sort of more elegant way to do that. A really bad way to actually solve this problem would be to introduce a pragma OMP critical here. And the reason for that is that this is where all of our work is. And so if we're making our threads wait to do this work, you're going to get incredibly slow code, basically. You're not going to have any speed up compared to serial. So we're not going to do this either. Now, the really nice thing about OpenMP is that when you're doing for loops, there's a way to do what they call reductions. Basically, what this reduction clause is going to say, we're going to be taking sum. Sum is currently a shared variable, but basically what this is going to do is it's going to say to each thread we're going to give more of a local sum. It's going to do this for us automatically, and at the very end we're going to elegantly add them all up so that we get the right answer. So this basically takes care of splitting the memory privately in the way that we should have amongst the threads, and then adding up to the global memory. So let's do this. And we can do that. And you can see that we're back to actually computing the right number. Now that we have this example, let's now start talking about scaling and how much this actually improves your life. So algorithms can be what are called embarrassingly parallel. So this is embarrassingly parallel in the sense that none of the threads actually have to talk to each other until the very end of the calculation when you actually do the reduction and sum up all of the local sums. Of course, as you're probably thinking, there's plenty of examples where it's not that trivial. But for embarrassingly parallel tasks, the theoretical maximum speedup would be sort of dividing out the total serial time by the total number of threads that your program is using. Now, that's a theoretical speedup, and it's not true in practice because there is overhead in spawning threads. And to see that, we're basically going to track how fast our program is, right? So we're going to get the wall time, which is basically this will give us some quantity in seconds from the CPU. And that's actually sort of arbitrary. We'll also get the end with this same function from OpenMP. And so their difference will tell us the time it took in seconds for the task to be finished. Well, this is starting to get a little cluttered, so let's do make demo now. Okay. And let's do OMP underscore num underscore threads is equal to 1 / demo. And let's give ourselves a big number so that it actually takes time to compute the quantity. So now that we have this, what we can do is this number should be about twice as fast. And it's not quite there, right? So twice as fast would have been 0.45. But you can see that perhaps due to the triviality of this problem, this is not, 6 times slower than this, right? And basically what we're seeing is diminishing returns to more and more threads. These are my physical cores, by the way, so I think if I go to 7... Oh, it's still getting faster, actually. Let's go to 8. 9. Because I have 12 total threads. 10. Let's just jump straight to 12. Okay, so you see that 10 is actually slower than 12. What did 11 do? Also, this isn't like super... Yeah, this isn't super rigorous, by the way, because, I mean, these are almost surely not good. These will always change, and you should really average over these types of things. Like, this is almost like empirical. You need to sample this observation. But basically, the idea that I'm trying to convey to you is that there will be diminishing returns, especially if your problem has sort of like a triviality to it. If the calculations you're doing in the threads are too small, and that's certainly what we're doing here. So if you want to keep the embarrassingly parallel speed up, the thing that you do inside the loop has to be complex. Otherwise, overhead will eventually take away your returns. Or the total number of things in your for loop needs to be bigger. So that's basically all I wanted to tell you. This was a quick crash course in OpenMP, and hopefully now you're at a point where you can start experimenting yourself. This is a huge speed up to productivity if you're writing scientific software. Or you're trying to solve problems with scientific computing and you have to write your own functions. And there's certainly more to be learned about OpenMP. For example, something that I didn't cover is that you can actually customize the schedule of the for loop and how tasks are distributed amongst the threads. But that's certainly a topic for another time. I wanted to keep this as self-contained and minimal as possible. So if you haven't already, please hit the like button and certainly feel free to leave a comment below. Thanks for watching, and I'll see you next time.